Welcome to Appendix C of our Radio Design 101 series. In this video, we're going to talk about constructing radio frequency circuits, starting with the simplest point-to-point wiring, moving on to printed circuit boards, and then really concentrating on the benefits of using two or more layers on a printed circuit board. And we'll explain what this diagram means and why it matters to you. So really we're talking about the how you make the circuit boards or whatever construction technique you're using. But most important, we're talking about the why. And that's something I haven't seen in other videos on YouTube. So that's what we're going to do today. So here's kind of an outline of some key issues. When you're building a radio frequency circuit, you need to be concerned about electrical issues, but also mechanical and thermal. We're going to concentrate on the electrical in this video, in particular the capacitive and inductive parasitics. And in the main Radio Design 101 series videos, we looked at those component parasitics in terms of how the impedance changes with frequency. And the trick with radio frequency design is that as you go higher in frequency, things get more difficult and you have to pay more attention to things. So that's what we're going to discuss. In particular, at VHF and above, component size really starts to matter, and the size of the circuitry, the interconnection links. We're going to discuss that in conjunction with PCB ground planes, printed circuit board ground planes, and shielding. And you may have heard of microstrip traces or coplanar waveguide. If you haven't, don't worry. We're going to talk about those and define those and why you need them. We build our circuits with transistors and integrated circuits and inductors and capacitors, but we also end up building things we don't think about, what are called parasitic couplings from one circuit to another. And to understand the effects of those on our radio frequency circuits, we model them as capacitance from one place to another. And it's not a capacitance in your circuit design, it's one that really comes from the layout or the construction of the circuit. And on this channel, there's another video I'd strongly encourage you to look at called Nano VNA - Measuring RLC Components. And in there, we talk about the fact that there can be capacitance between any metals in a circuit. And I explained this blob here and this blob here. That's just to show that it doesn't have to be a physical device. It could be traces, it could be part of the casing, anything. What we do know is that capacitance conducts signals at high frequencies. In fact, the reactance or the impedance goes down as the frequency goes up according to this equation that you probably know. And here's some examples of impedances. Let's say that you've got a couple of things that produce 1 picofarad of capacitance between them. At 1 megahertz, we probably don't have to worry about it too much because the reactance is around 160,000 ohms, 160K. And I say 160 instead of 159 because we're just looking for ballpark estimates here. I don't know that it's exactly 1 picofarad between your two circuits. The point is, at low frequencies, at 1 megahertz, it's so high that it doesn't affect your circuit. But as you get up to 1 gigahertz, 1 picofarad of coupling between two parts in your circuit can be an impedance of 160 ohms, not 160K ohms. Now, 160 ohms is getting to be pretty significant because most of the sub-circuit node impedance and IO impedances in your circuit are probably between 10 ohms and 10K, and this is smack dab in the middle. So suddenly you've got a circuit component that is affecting things that wasn't intended. So that's our problem. Similarly, in that video, we talk about and demonstrate with some measurements inductance from just currents going through wires. Don't worry about this particular diagram. It'll be explained in that video if you want to watch it. But the point is, anytime you have current going through a wire, any trace, or actually just a component, you have magnetic fields created. And what does that do? Well, it creates an inductor. And at low frequencies, no big deal. But at high frequencies, the reactance or the impedance goes up with frequency. So a relatively modest 10 nanohenries no big deal at 1 megahertz because it's 0.063 ohms. But at 1 gigahertz, 10 nanohenries will be 63 ohms. And again, this is in the middle of the range of component values that we have in our circuit and we're trying to design with, and suddenly there's another one which is not intended to be there. This is why things go wrong. So what about these values that I picked in my example? 1 picofarad, where did I get that? And 10 nanohenry, where did I get that? Well, here's an example of an early computer circuit board. This is actually out of a 1960s circuit card that was part of the Apollo moon landing ground support equipment. At least that's what I'm told by the eBay people that I bought it from. But let's take a look at it. It's got diodes and transistors and resistors. So it's diode transistor logic. If you flip the circuit board over, this is what you've got on the back. And it's a printed wiring board just made to make it easy to connect things together. And there's a few traces on the top, but most of the traces are on the back side. And if you just take a couple of these together, you'll notice that they're right next to each other the whole way. And how long is this? Well, it's about 18 centimeters. So to get a ballpark estimate of the capacitance between two traces, call your attention to the picture on the left over here. We've got some metals. They're right next to each other. I kind of drew this to look like a parallel plate capacitor. These are not parallel plates, but if you work through the physics of it, it doesn't really matter. We can still use as an estimate, C is approximately equal to the parallel plate capacitance formula, which is the permittivity epsilon effective here times the area of one trace versus the other trace. Well, the area is the length times the width, as it says, and the separation between them. And again, this could be off by a factor of 2, but I don't really care. When I work this out, I got 2 picofarads. So there, I mean, even if I'm off by a factor of 2, it's 1 picofarad. And in the lower part, I'm looking at the inductance along the traces as signals go from one end of the trace down to the other end. There's current flowing through that, and it generates magnetic fields. And there's a formula I put down here without proof, but it's a good formula, and we will talk later about how you can prove it if you want. The inductance is about 1 nanohenry per millimeter. That's a very ballpark thing, again. But we've got about 20 centimeters or 200 millimeters, and so that's 200 nanohenries. That's a lot. That's 20 times what I estimated over here. So this is where the stuff comes from. And this is why these kind of circuits can't work above a few megahertz. So the clock frequency in this computer was probably very, very low. Now, in the Radio Design 101 series, we were working at VHF, in particular 100 megahertz, but in any case, very high frequencies as opposed to HF. And we used some little proto boards that had circuits on the top, but we also had a backside ground plane. So you can kind of see the backside here. And once you've prototyped some circuits, you may want to build a circuit board to make it nicer. And this is a circuit board I built for one of the circuits shown in Epilogue 3 of the Radio Design 101 series, but it uses a ground plane. So this is the circuit board drawing tools view of the board. This is the actual board. There's a top side and a back side. The top side are the red material here, the red traces. The back side is a ground plane. It's a flood of copper, and it's blue. So we've put a ground plane below the traces, and it turns out, as we're going to show, that the ground plane reduces electric and B field couplings between traces. And it also reduces the inductance per unit length, but it's not a huge change. But the concept of per unit length is going to become very important as we move on. We've got to consider the inductance and capacitance per unit length. And at UHF and above, we end up basically with traces acting like transmission lines on the circuit board. In the circuit board drawing tool, we can look at it from a top-down view, as we just did, or, this is from KiCad, PCB editor, we can ask it to show us a 3D view, and that's what we're looking at on the right here. On the top, there are these traces that lead to surface mount components, etc., etc. Here's a chip over here. But let's look at the backside. The backside is the blue, and I said it's a copper ground plane, and that's this white material down here. On this edge is an SMA connector, J1, where the RF comes into this particular circuit. So it has these landing patterns to solder to, and then that transitions to a trace that goes over to a capacitor, and then a little bit of trace that goes over to an inductor, and so forth. Now, remember what we said. Anywhere two metals are close to each other, there's capacitance between them. And anywhere current is flowing through a wire or whatever, you get magnetic field wrapped around it, and that creates inductance. So, here we have capacitance from, say, this landing pattern here to the backside ground plane. If you look at it, that's almost clearly a parallel plate capacitor. So I hung a little capacitor symbol here from this node or this point in the circuit to the backside ground plane. And then there's more capacitance over here. And what we do is we conceptually subdivide a longish trace into something of short segments. And so there's capacitance here, there's capacitance in this section, there's capacitance here. There's actually capacitance all the way along, which is why we talk about capacitance per unit length. And a very rough estimate would be about 1 picofarad per centimeter. And as we introduce an RF signal into this circuit, this capacitance and this capacitance, as well as all the loading here, draws current from the source, and that goes through this metal, and that's why I put an inductor here. So as the signal goes along, it encounters inductance all the way down. And I say that's very roughly about 5 nanohenries per centimeter. It varies depending on how thick the board is, how nearby the ground plane is. But these are very good ballpark estimates. The upshot is we don't have traces only. We have basically transmission lines. A transmission line is something that can be modeled by capacitance, inductance in this sort of ladder structure. And we didn't intend this to be a transmission line, it just is. And here's some of the main parameters that we'll care about when we start treating it as a transmission line. It takes some time for the signal to get from here to down here and then on further. And how much time? Well, it depends on the velocity of propagation. That's what V sub P is here. And I'm saying it's very roughly, in a circuit board like this, about half the speed of light. And if you've dealt with transmission lines before, oh, by the way, coax is a transmission line. And so if you've dealt with that before, you know that the impedances of transmission lines are often somewhere between 50 and 100 ohms, that kind of thing. Here, using these values, I calculated it out. It's going to be about 70 ohms. I can make the traces wider and make it a 50 ohm line if I want. Anyway, it just depends on your circuit. But the point is that anywhere you have connections on a circuit board, in particular traces, they are transmission lines. Now, we can simplify it as a bunch of small inductances and capacitances, depending on the circuits that are around it. So here's a summary of what I was just trying to talk about there. This is from a 2-page class handout that was given in the senior university design class that Radio Design 101 was built around. Let's take a quick look at the resistors. Now, in the old days, there were what are called leaded components. So we had a resistor here with some color bands on it, etc. But it had some wires coming out the two ends that we solder onto the circuit board, and then they go on to something else. In the schematic, we draw it like this, and this is the way we think about it. But at radio frequencies, we always have to be on our guard that there might be enough parasitics to create a problem. And so this is the model that we should be thinking about, and possibly including, depending on which of these extra parasitic components matter. So what's this inductor here? Well, that's because you've got wires here and you've got traces on a circuit board. The problem doesn't end at the wire when it connects to the circuit board. You can treat those traces also as small inductances. And here I wrote it as 15 nanohenries per inch. Now, in the upper right here is a surface mount component, and you might think that, well, it doesn't have leads, so it doesn't have any inductance, but that's not true because, well, when current flows through that, it also creates a magnetic field around it, but there are traces on the board that extend out from these locations. So we always have to worry about parasitic inductance and compare its impedance to the resistor value, for example. In addition to that, we're going to have a component that's going to be near other stuff, in particular a ground plane below it, so there could be some capacitance from the resistor down to ground, and there could be capacitance between the two sides of the thing like this, or between this wire and this wire. Doesn't look like it because they're not in parallel, but we know from electromagnetics that you have these arcing fields that go from one side to the other, and so that's going to be some capacitance. These are very, very rough estimates. The point is in the diagrams down at the bottom. As we go up in frequency, the impedance of this inductor may matter. At low frequencies, it doesn't. So if we have a 10 ohm resistor at low frequencies down here, the impedance, magnitude of Z, looks like 10 ohms. But at some frequency, say, I don't know, a gigahertz, depends, then this starts to go up. The impedance starts to go up. And this can actually happen at 100 megahertz. What about the capacitances? Well, if you got a 10 ohm resistor, the reactances or the capacitances are probably several hundred ohms or more, even at a gigahertz. So we can kind of ignore those. So it's not as complicated as it looks. We really treat it as two regimes. Low value resistors, we care about the inductance. And at high value resistors, then this inductance, which may only be 20 ohms, if you got a 1K ohm resistor, we don't care. But this capacitance from one side to the other may decrease the overall impedance of the resistor as shown in this curve. And similar comments can be made about the PC board trace, the microstrip trace, the transmission line. So here's a trace above a backside ground plane. When we're drawing the schematic, we draw it like this, but we really need to think of it like a transmission line sometimes, depending on the frequency. And as we've discussed, that transmission line is a ladder structure of capacitances and inductances. We subdivide the trace into small segments, and they each have capacitance to ground in this case and series inductance. So here's the transmission line. And what happens if we stick a 10 ohm resistor down at this end of the line and we look in the other end? So imagine there's a resistor here, and then we put a via to ground, and we look in this end and we see what the impedance looks like. Well, if you think through this, using what I just said, you can derive these kind of curves. If you had a 1K ohm termination down at the right-hand end of the line and you look in the left, it may look like this. It may roll off. And I'll let you think through that. I'll pause here for a second if you want and think about it. Moving on, you may have heard about the characteristic impedance of transmission lines, coax or what have you here. It is a microstrip trace on a circuit board. It has a characteristic impedance Z0, and if the terminating resistance is the same value as the so-called characteristic impedance of the line, then you could have the resistor at this end and look in this end, and magic happens. It's as simple as looking like the resistance again. So this is what the plot looks like. And over on the right of this slide, I'm trying to give a hint at when this transmission line behavior matters. It matters when the length of the line is about 1/10 of a wavelength or more. So a wavelength is c over f, speed of light divided by frequency in hertz, times the relative velocity of propagation. And in this slide I said Vp is 0.5 times c. That means that the relative velocity of propagation here is 0.5. All right, anyway, I crunched this, and it turns out that at 1 gigahertz, I have for lambda over 10 about 1.5 centimeters, a little more than half an inch. So if you've got traces connecting circuits that are that far apart, then you might need to think about the transmission line behavior. Conversely, if they are closer than that together, then you can probably get away with just thinking about series inductance and shunt capacitance issues. So you can really avoid the complication here if you condense your circuit. Or if you're working at lower frequencies, say 100 megahertz, then this would be 15 centimeters, and something like this trace right here, I probably don't have to treat this as a transmission line. This is a 100 megahertz filter I was designing, and this is only a couple of inches. I'd only have to worry about it if it was, say, 5 or 10 inches long. But I might still need to consider the series inductance of something like this. And these parasitics really matter for capacitors. So we often use capacitors as bypass capacitors in a circuit, and the series inductance of that from leads or the component plus the traces may matter. And again, what that means is when you're designing an RF circuit, you need to be aware of these parasitic capacitances and inductances. And especially when you're constructing it, when you're doing a layout, for example, you need to worry about it. So this is a Q-enhanced filter that was talked about at the end of the Epilogue 3 in the Radio Design 101 series. This is a PC board level version of it. And it involved a common base RF amplifier. So here's the common base amp and the tuned circuit load. The input comes in on the emitter, the output on the collector, and the base has to be AC grounded. So C4 here is a bypass capacitor on the base, but it's only a bypass capacitor if we lay it out right. If we don't, then series inductance in this trace is going to make it possibly an inductor rather than a capacitor. You have to work out what the reactances are. The key is to make sure your bypass capacitors are right next to your components that need to be bypassed, so you minimize the inductive parasitics. Q1, the amplifier, in the layout is down here on the right bottom, and you'll notice that, well, this is the emitter, this is the collector, top terminal here is the base, and that goes over to C1, which then goes to a via to the backside. So you'll notice that the length, the distance from the base terminal of the transistor through the capacitor over to that via and down through the via to the backside is the length we care about. And I've minimized it by putting this capacitor here. There's a resistor in parallel with it, R2, and I could have been silly and put it close to the transistor, but that's bad. We need the bypass capacitor in this position, so that's why the resistor's over here. Similar things can be said about supply bypass capacitors. There's one here, there's another here. At the schematic level, it looks dumb, but we know now that this one is probably here to locally bypass these two transistors, and it's buried down here, whereas this one is over here. And before we leave this slide, let's note that I've got an arrow pointing to the inductor. Why is that? Well, that inductor is here in the layout, and it's 100 nanohenries, but that's what the manufacturer measured from this terminal to this terminal. But there is, in fact, an extra trace length here. There's the length of C6, and then when it comes back to this terminal. So that's in series with the 100 nanohenries. So maybe it's 110 nanohenries, but that might matter a little bit. So you need to think about these things. Now, in the classroom, when I presented this material, I would do demos. And this video is going to be way too long if I do a demo at this point in it. We got lots more to cover. However, on this channel, we already have some demonstrations, and these are taken from basically things we did in that classroom. So I'd encourage you to look at these on this channel. An easy way to find them is just to search for these titles under the Megawatt KS channel, or you can go to the ecefiles.org website and find the series on measurements in nano VNA. And in addition to demonstrations, it's important to have some real-world examples, right? So here's what's coming up. We're going to look at some older radio designs and the problems, and then we're going to go into the higher frequency region. But at this point in this video, I realize I've thrown a lot at us here. In particular, we're talking about these transmission lines and parasitics and so forth. The real question is, what do they do to us? What is the problem? Well, remember this slide. These are some of the problems that those parasitics create. They also make our circuits not work sometimes. So we're going to look at, for example, why construction techniques changed over the years from tube-based designs to transistor and integrated circuit designs, but also to multi-layer circuit boards. But we've covered a lot today, and I think I probably need to stop this video here, and we'll cover this material in a part 2. Now, it's not just examples. It's material that shows in a detailed way how parasitic capacitances that couple from one trace to another one can interfere with the operation of circuits. And so we're going to cover that in detail. This is one of the things that is really not out there, as far as I can tell, in the YouTube video world. So we'll look at one-layer printed circuit boards and the problems that result. We'll look at two-layer circuit boards and why the ground plane helps. And we'll do that using some fairly simple circuits. They're approximate circuits, but they get the point across. We'll also show some examples of traces on circuit boards and how they couple to each other in terms of real-world measurements, and we'll cover this. And then we'll talk about shielding and how that works and why it works. Because if you know why something works, then you can figure out how to make it work in your particular scenario. That's why knowing why really matters. And we'll touch on what we can do with four-layer circuit boards. And I'll briefly talk about KiCad and various fabrication companies. This is one of them. And talk about what the so-called layer stack-up looks like on a four-layer board. And what it might look like in an integrated circuit. There's actually a ground plane right here because there's a bunch of digital circuits and there's sensitive RF circuits here. And finally, we will look at the 77 gigahertz automotive radar teardown that I showed in class to demonstrate how people do stuff at these super high frequencies. Okay, so that's it for today. I really hope this was useful, and I hope that you come back when I get the next one out, maybe about a week. And I think that that extra material showing how you can model the coupling from what we call an aggressor circuit to a victim circuit is created. And then that will guide you in understanding why multi-layer circuit boards work and when they work and when they maybe don't work. Okay, thank you.